Hey class, um, welcome to another lecture video. I'm deciding to take a bit of time that I have and record this beforehand. One, to give myself a little practice, and two, just to maybe have a bit better quality on the videos. I'm thinking about maybe trying something, hopefully after this test on Wednesday. Maybe I can record better for those who can't be there or just to want to review the lectures, but I will do this for now. So yes, anyway, we have two topics today. So we'll be covering sections 2.8 and 2.9. Okay, and the first topic we're going to be discussing is something called implicit differentiation. Okay, well, what does that mean? So we've already talked about a lot of cases, right, where we've been working with functions, right? We started out the chapter by talking about functions and how we know something's a function or something's not a function. And we've also done all the rules for those in terms of our kind of simple multiplying with polynomials, dividing, etc., like rational functions. But there's still a case where we could use derivatives that we haven't completely figured out yet. And that is the case where, so let's consider the following graph. Of a circle, okay? And the equation of the circle we'll say is x squared plus y squared is equal to 1, right? Now, typically, right, this isn't a function, right? Just as is isn't a function, right? Because it clearly doesn't pass the vertical line test. And so normally what I would want to do is I want to be able to write this as a function, right? So what I would do is I would say, okay, let's have, I'm going to solve for y, right? So I'll get y squared equals 1 minus x squared. Taking the square root, you would get y equals. Now this is where it gets important, right? Because if I just say the positive square root of 1 minus x squared, what does that give me? Does that give me the whole shape, or does that just give me part of the shape? Well, it only gives me the top half, right? That's all this equation tells me. So if I want to get the top half, this is okay. So let me write top here. But if I want to get the bottom half, right? I would have to write this equation as y equals negative square root of 1 minus x squared. Okay, now you might be seeing where I'm going with this, right? But when we're finding our derivative, right, this absolutely, which one, like how we find the derivative on this shape, right, or like the tangent line to the curve at a specific point depends primarily on where exactly it's at, right? So for example, if I was dealing with, if I want the slope of the point 1/2, let's see, is that a good one? With working with one, it's probably a little more difficult. But if I just use x is 1/2, right? So let's say I have the point 1/2 and the square root of 3/2, right? Well, this is on this half of the circle, so I would have to differentiate this equation in order to get the tangent, kind of the slope at this point, right? But if this was a minus root 3/2, right, then I would have to go to this one, right? So what's happening, right? I can't, no longer can I just use one equation, in this case at least, to get the slope at each point on that curve, right? I have to use two different ones and I have to go between the two of them, right? But what implicit differentiation allows us to do is it allows us to not only have the derivative depend on x as we normally expect it to, right? You know, like kind of in our typical function form, but we can actually also find derivatives for things that aren't functions, for things that maybe we can't write nicely as just y equals something. And the way we do that is through this process that we call implicit differentiation. Okay, so to check that, right, to make sure we're talking about this right, first let me pull everything up here because we want to be able to use our example here, right? So remember, so we'll say top is y equals square root of 1 minus x squared, and bottom is y equals the square root, negative square root of 1 minus x squared, right? So we have these two equations, right? And we're wanting to deal with the points, the 2 points. I want to find, so I'm going to write find the slope at 1/2 root 3 over 2 and 1/2 negative root 3 over 2. Okay, so let us take the derivative of this function, right? So what I would do, right? So no matter where if we have the plus or minus on it, I can rewrite this. So I'll write plus or minus in front. It's just a change of the sign is 1 minus x squared to the 1/2, right? Now this is an easy example how they're both sides are pretty closely related, but oftentimes you may not always have that. So if I'm taking the derivative of this, right, we have to use chain rule. And chain rule says that I take the power, I multiply it down to the front, right? So if it's plus or minus, it'll just become, we get plus or minus 1/2 times 1 minus x squared, right? Chain rule, I leave the thing in as it is, right? Or general power rule, which is chain rule. And then I subtract 1 from the power. So that's going to become minus 1/2, just like that. And then I multiply by the derivative of the inside, which is 2x. Okay. So in other words, so this 2 and this 2 will cancel. If I just after the derivative of this thing, this would be perfectly fine. I'm doing this simply for the sake of helping us to kind of work through this problem a little better. So the 2 and the 2 cancel out, and then I'm going to have x, and then this is negative 1/2, so that can come to the bottom, and then the 1/2 is the square root. So this is actually the same thing as plus or minus x over the square root of 1 minus x squared. Okay, so then I would have to say, okay, well, I want the top half. Okay, so I need to use, I want this point, right? Which means that I would need to use the top half. Which means that I only want the plus in this case, right? So we're using the positive x, right? So if I'm finding the derivative of this function at 1/2, then I have to do 1/2 over the square root of 1 minus 1/2 squared, which is going to be 1/2 over, let's see. So we have 1 minus 1/4, which is 3/4, which is the same thing as 1 over 2 times 2 over root 3. Taking the square root of this is square root of 3 over 2, and then keep change flip. The 2 comes on top and 3 stays down here. So we get 1 over the square root of 3. Okay. And then plugging in, if you want to get the slope of the other point, I would have to plug it into, instead of the positive version, the negative version instead. Okay. So depending on the point, I have to change what I get, right? So then in that case, so the slope of this one ends up being 1 over root 3, and the slope of this one ends up being negative 1 over root 3. Now, instead of doing all of that, right, kind of having to worry about this chain rule and all that, at least in sort of bigger scheme, let's do it a different way. So let me rewrite the original equation, which we said the original equation was x squared plus y squared equals 1. So I want to just take both sides of this equation and take the derivative of it. Maybe I'll put that in orange. Now, you might be asking, okay, well, I can take the derivative of x squared. I can take the derivative of 1. How do I take the derivative of y? Right? Well, what we can do is we can assume, right? Safely assume, that is, right? Especially since we were able to solve for it. In most cases, you would be able to solve for it maybe in some way. That y is a function of x, right? So in this case, I can just use, right? And this is why we learn chain rule, right? It's because I can just use chain rule on this, right? So so what I'm saying is that, right, if y is f of x, right, that if I'm taking the derivative of a function of y, let's say g of y, then this is the same thing as the derivative of g with respect to y times the derivative of y with respect to x, right? Because then that would exactly give me the derivative of 1, right? So I just multiply by the derivative of the outside. More specifically, and I'll write this equation in blue, the book gives this nice formula. I would encourage you to make sure you understand this. Again, maybe to write it in a form that's more familiar, you might have seen something like this, where I have dy over dx equals dy over du times du over dx. And this is when y is a function of u. This is the chain rule. But, right, we want to be able to, right, why do I want to do this? Well, I want to be able to get the derivative of y with respect to x, right? I'm still wanting to see how the rate of change is y over x. So my goal is to get this, which is why I want to learn a formula like this. Now, the book gives the generalized power rule again, but instead this time, it's talking about y to a power. So anytime I'm taking the derivative of y to an n power, this is the same thing as n times y to the n minus 1 times dy over dx. Okay, so you probably have seen that rule before. That is chain rule, right? Where this is the generalized power rule, and we used to use u, right? But now it just says y. Because in this case, we don't really know what the function is in this case. Generally, we might know u is a specific function, but y, we're not sure what exactly that function is. Because sometimes we don't know. We'll see examples where it's going to be really hard to figure out how to solve it. And so in this case, we can use this rule. Okay. Now, how does this help us? How does this help us here? Well, it's going to help us because now I know how to take the derivative of y to a power. I use this formula, right? So the derivative of x squared, right? We use power rule in that. And again, when I take the derivative of the sum, I just take it to each part. So the derivative of this thing is going to be equal to 2x, right? So the 2 comes down to the front, and then I have x to the first power plus, now y squared, right? So if we say y squared, right, that means I pull the 2 down, just like I would for the x. So the 2 minus 1, so it becomes y to the first power. But then I have to multiply by dy over dx. Okay. Good. And this is equal to the derivative of 1. What's the derivative of 1? Well, it's 0. Okay. So now what's my goal here? What was I finding? The derivative, right? So to solve for the derivative, let's get it by itself on this side. So I'm going to subtract 2x from both sides. So this is going to give me 2y dy over dx equals negative 2x, which says that y, and then we want to, so I subtracted 2x here. And now I want to get the dy over dx again by itself. But now the only thing that's with it is multiplying, so I have to divide by 2y. So that leaves me with dy over dx equals negative x over y. So now what has happened is we have found our derivative in terms of x and y. So if I need to find the slope at that specific x and y point, then I just take that x and y point and plug it in, right? So for example, if I want the slope at, so if I want dy over dx at the point 1/2 √3/2, then I simply just plug in, oh, by the way, this should be, sorry, this should be a minus here. Let me think about this real fast. I do something. Okay. I think I made a small mistake earlier. So I want to apologize for that. Most of the work is good, but let's see where my error was, right? So when I took the derivative originally of just each of these y functions, right? It was, we said plus or minus, depending on whatever it is, 1/2 times 1 minus x squared to minus 1/2 times, and then I said 2x, right? But actually what should happen is this minus, right? When I take the derivative of the inside, this term becomes 0, and this term becomes the derivative of x squared, which is 2x. So we get minus 2x. So there should be a minus here. So then when I simplify this out, like I did before, this should actually end up being, depending on which you use, top or bottom, it should actually be minus, like, so now what's going to happen is so when I solve this, I'm going to get minus plus x over the square root of 1 minus x squared. So all this means, right, the only difference that's changed is that basically if I'm using the top, then I should be using this negative instead. So really this slope should be minus 1/3. And if I'm taking the derivative of the bottom, then that slope should be a positive instead. So this should be positive 1/3. Okay, so sorry for that confusion. Hopefully everything's still okay. It's going to be the same thing, so apologies for that again. But yeah, so the sides flipped around. But all that happened is that these two positive terms gave a negative, and then the positive and negative here gave the positive here, which now will make sense when we talk about doing the derivative inside this function. So when I take the derivative of that, I'm going to get negative 1/2 over √3/2, which we've actually worked that out a little bit earlier. This is the same thing as negative 1/3, which is exactly what this needed to be. And the derivative at 1/2 negative √3/2 is negative 1/2 over negative √3/2, which these minuses cancel out, and we're left with positive 1/3, which is exactly what this needs to be. Okay, so you notice that we just had one derivative for the whole shape, even though it wasn't a function. And that's okay. That's nice, it works out. And so we can pull all this stuff together and make it work. So yeah, there's the big example for how kind of taking doing implicit derivatives work. So now let's go through some examples to practice this idea. So let's see. So we'll take one example. Let's see. We'll do example 1. And probably just the first term, right? So let's re-cement the idea, like of what we're doing, right? So examples. So example 1, right? In the book, we are given that 3y squared, or sorry, 3y cubed, apologies, times x, or sorry, equals x. Sorry, I can't speak very well today, apparently. That's all right. So I want to take this thing and find the derivative of it. Okay. Now you could try to solve this for y again, but might be a little more difficult, might look a little weird. So why don't we just try to leave this and find the derivative implicitly? Okay. So the way I do that is I'm going to take the derivative of both sides. Okay. Now, remembering our rule, right? So the general power rule here, which is the same as the other one, but maybe it's more helpful to see it this way. The derivative of y to the n is equal to n times y to the n minus 1 times dy over dx. So when I use that here, right, this is going to leave me with, and I'll put an arrow here. So, right, so I leave the 3. The 3 is just going to come out, stay by itself. Nothing happens with it, right? Just like with the normal derivative. And then we take the derivative of this y cubed, and then it's equal to the derivative of x, which we know is just 1, right? Now from here, the derivative of y cubed is going to be 3y squared, and we want this to be equal to 1. So what is this? So, 3y squared times the derivative of y with respect to x, and this is equal to 1. Okay, so then I want to find the derivative, of course. So I divide both sides by what's here, which is the same thing as 9y squared, and that's going to give us that dy over dx is equal to 1 over 9y squared. Okay, so if you're given an xy point, right, say, let's say you're given the point 3, 3, 1, and I want to find the slope at that point. Then I just take 3 and 1 and put it in, right? So dy over dx of 3 and 1 is going to be 1 over, now there's no x to put in here, right? So I can't really put 3 anywhere, but I can put 1 in for y. So I'm going to get 1 over 9 times 1 squared, which is the same thing as 1, 9. And so at the point 3, 1, we have a slope of 1. Okay, cool. There's a couple of just other examples with one if you want to look at them. They're basically saying the same idea, but yes. So now our next example is going to be a little bit more complicated, as you might expect. So we have 3x squared plus 4 times x cubed y to the 4th plus 2y is equal to 4. So this is example number 2. Okay, so again, we want to take the derivative of everything here, right? So what's the derivative of 3x squared? Well, that's going to be 6x. What's the derivative of, okay, let's go back to this term. What's the derivative of 2y going to be? So remember, again, I'll write the rule here one more time. I'm taking the derivative of y to the n. This is the same thing as n times y to the n minus 1 times dy over dx. So in this case, we have y to the 1st power. So the 2 is just going to come out, right? It's kind of just going to phase out on the outside. So I'm going to have plus 2. And what's the derivative of y here? Well, the 1 would come down times y to the 1 minus 1. 1 minus 1 is 0. So we get in 1 times 1. So we just get 1, right, times the derivative of y with respect to x, okay? So essentially what you want to do is you want to, whenever you're taking the derivative of anything with y, you want to treat it as if you're taking the derivative of x at first, right? Do all your x stuff, and then just throw on a dy over dx at the end, okay? So that y to the 1st power just becomes, the derivative is just dy over dx in the end. What's the derivative of 4? Well, it's just 0. Okay, now here, remember, I can't just combine these two powers together. And this isn't just the derivative of each one, right? This is a product rule problem. So I have to use product rule. So to use product rule here, we'll call this U and call this V. So we're going to have plus, and then I have 4 times U, right? Remember product rule. U is x cubed times dv over dx. So dv over dx, right? I take the derivative of y to the n power, right? Which is going to be, actually, let me make sure I want to include this 4 inside this u. That'll be easier. Okay, the derivative of y to the n power, and 4 in this case, we're going to bring the 4 down, y to the 4 minus 1, which is 3. So we get 4y cubed dy over dx plus v, right? Which I'll put over here, times the derivative of u. The derivative of u, right, is just 4x cubed. Or sorry, 4x cubed is u, right? So the derivative of that is going to be 4 times 3, which is 12, x to the 3 minus 1, which is 2. So we're left with 12x squared y to the 4th plus 2 dy over dx equals 0. Okay, so here we just use power rule, generalized power rule, constant, and then this was the product rule, kind of combining with our generalized power rule we have. Okay. Now again, what am I solving for in these problems? What's my ultimate goal? It's to differentiate. So I want to find the derivative. So to find the derivative, I need to get this guy by itself, right? So let's circle our terms that have a dy over dx here and here. Okay. So if I want to solve for those terms, I need to get them by themselves first. So let's move everything that doesn't have that dy over dx and then move it to the other side, right? So I'm going to take the liberty here real quick. I'm going to rewrite 4x. So I can multiply this 4 and this 4 together to give me 16. So I get x cubed y cubed. And I'm going to rewrite dy over dx in orange. Okay. Plus 12, or sorry, plus, so I need to subtract the 6x from both sides, and I need to subtract the 12x squared y to the 4th from both sides. Okay, so, and then we're left with plus 2 dy over dx. And this is equal to, so we're going to have minus 6x minus 12x squared y to the 4th. Okay. So what do these two terms have in common? Well, there's a number that they both have in common, of course, but the thing that's more important is that dy over dx, right? So what I can do is I can take that dy over dx and factor it out. So I get dy over dx times, and then we have 16x cubed y cubed plus 2. Okay, make this a bit shorter here. Maybe I might put 2 people there, so just enough. Because we're not taking the derivative of this thing, just multiplying with it. It's equal to negative 6x minus 12x squared y to the 4th. So if I want to solve for dy over dx, all I need to do is divide whatever is not dy over dx from both sides, which is all of this term. So I'm going to take both sides and divide it by 16x cubed y cubed plus 2 divided by 16x cubed y cubed plus 2, which leaves me with dy over dx being equal to negative 6x minus 12x squared y to the 4th power divided by 16x cubed y cubed plus 2, which you can fiddle around with this. The book will take, all these are even numbers, so they're all divisible by 2. So I could divide by 2 in the top and bottom, and maybe I can move this minus off to the side a bit. So I can rewrite this dividing by 2 in the top and bottom and kind of factoring out the negative. I get minus 3x plus 6x squared y to the 4th power over 8x cubed y cubed plus 1. And so that would be the derivative in that case. Okay, so instead of trying to solve this crazy function for y, which is very hard to do, we can just find the derivative using both our x and y point that makes that function work. Okay, so hopefully that made sense. This is probably what most of your examples might look like as you go through and do these sorts of problems. But yes, so now it gives a kind of a harder example where you have to do plug in the value, and you can feel free to practice that if you want to. The book will explain it. I'm going to do the other example just for the sake of time, so I can get to do the other lesson real quick as well. So, well, I guess I have a third example, but the last example for this section says that it says find the equation of the tangent and normal lines to the parabola y squared equals 3x at the point 3 and negative 3. Okay, so this is very important to remember, okay? Because I will ask for this. You need to find the tangent and the normal line. Okay, so tangent line, we know what that is, right? So let's start there. We know how to find a tangent line, right? But let's bring up our parabola, right? So our parabola in this case, we have y squared is 3x. Okay, and I want to find the tangent normal lines to this parabola at the point 3, negative 3. Okay, so to find a tangent line, right, I need two things, the point and the slope. Well, we have the point, as always, generally it seems, but we need to know what the slope is. So what we're going to do, right, is solve for y, right? No, we're going to take the derivative just as it is, okay? So I won't write the rule again. Hopefully, I want to kind of start walking away from it so it's not always there. But to take the derivative of both sides of this, I'm going to get that the derivative of y squared is going to be 2 times y, right? Let's take the derivative as if it was x, but then I need to add on a dy over dx. Okay, and we want this to be equal to the derivative of 3x, which is simply just 3. Okay, so then to solve for dy over dx, I simply need to take away the 2y, just like similar to the last problem. And so we're going to get that dy over dx is equal to 3 over 2. Good. So this is my derivative, right? And this will give me the slope, right? So I need to find the slope at this point. Okay, we're working on the tangent line right now. Okay, so let's emphasize we're getting the tangent right now. So to get the tangent line, I just need to plug in my value to get the slope here. Right? So I need to find dy over dx at the point 3, negative 3, which is going to be the same thing as 3, right, over 2 times y. There's no x, so we don't have to plug in this 3, but there's a y, which is this negative 3 in this case. So I need to multiply by minus 3 at the bottom. And so this is going to leave me with 3 over negative 6, which is the same thing as negative 1. Okay, so that is the slope of my tangent line. I have the point for the tangent line, and so now I'm going to use point slope form. which says that y minus y1 equals m times x minus x1. Here's m, and here's our point, x1 and y1. So when I plug in, I'm going to get y minus 3 equals m, which is minus 1/2, times x minus 3. Okay, so simplifying this out, I get y minus 3, so we get y plus 3 equals, and I'm going to multiply the negative 1/2 to both sides, to both values here. So I get negative 1/2 x plus 3/2. Okay, and then I need to subtract 3 from both sides, which will give us that y is equal to negative 1/2 x. What is 3/2 minus 3? Well, this is the same thing as 3/2 minus 6/2, which is negative 3. So we get negative 1/2 x as our final result. Okay, cool. So that is the tangent line. How do I get the normal line? Well, let's think about the normal line, right? So the normal line, right? So our curve, we have y squared equals 3x, which is the same. So, and we have the point 3 minus 3. So it's probably going to look something like this. Okay, so when we talk about the tangent line, right, you just found, it's gonna say that we're at this point here, right? So let's say that, well, actually, I guess it would be down below, right? So let's say that this is the point we just found, right? Or the point that it gave us, okay? And we just found the tangent line to that point looks like this, okay? The normal line, right, is whenever we say normal, that means that normal means that it's perpendicular. Okay, so for example, right, if I have this straight line, let me draw that across more so you can see it. If I have this straight line here, then a normal line to this straight line would just be that, right? It's at a perfect 90 degrees between the two. It just goes, if this is flat this way, then this is going to go straight up, right? So the normal line to that specific point should be straight out of it like this. Okay, maybe we'll color it orange so we can see it a little better. Okay, in other words, it is 90 degrees to our tangent line, which means what? That it's perpendicular to our tangent line, right? Now, who here remembers what happens? Like if I am given a line, how do I find the slope of the line perpendicular to it? Well, the way to do that, right, is first let's recognize, right? So this is our line here, right? Now this line is going this way. So its slope has changed signs and it's become positive, right? Because it's going up now instead of down. So the sign changes, but also this is kind of a slower slope, but this is building up, right? So what happens is that I kind of reverse the effect of it. So in a sense, the slope of this normal line. So if I have m, right, is the slope of a line. Slope of a line. Then negative 1 over m is the slope of the normal line or perpendicular. Line. Okay, so all I need to do to find the normal line is, first off, I'm going to rewrite this. The slope is now going to become my new m, essentially. If m was originally negative 1/2, then the new slope is going to be negative 1 over negative 1/2. Right, because just like from here, so I flip and I change the sign. So when I do 1 over 1/2, that would give me 2. So right now I have negative 2, but the negatives cancel out, so we get 2. So the slope of the normal line is negative 1 over the slope of the other line, right? So here's it clear. So if this is the slope of the line, then of the tangent line, I guess I should say, maybe that'd be better, tangent. Then negative 1 over m is the slope of the perpendicular line, the normal line to that curve at that point. Okay, so we use 2. So now I'm going to put 2 in for the slope instead of negative 1/2. So now that's going to give us that y minus negative 3, which again is going to be plus 3 equals 2 times x minus 3, which leaves us with y plus 3 equals 2x minus 6, which means that y equals 2x. What is minus 6 minus 3? Well, you add the two numbers together, so we get minus. So this is tangent here. Sorry. And this line here is. So that's how we find that. Okay, cool. So that is implicit differentiation. If you will give me 1 second, well, probably a little longer than 1 second, but let's talk about 2.9, which is a very short section. So I won't need to take too much of your time. Okay. Okay, so section 2.9, right, says higher derivatives. Okay, so maybe let's go back to 2.6 real quick. So maybe in 2.6 you had the question of, okay, well, we know that S is equal to V is equal to ds over dt, and A is equal to dv over dt. Well, if velocity is the derivative of S and A is the derivative of velocity, couldn't I get A by somehow doing the derivative twice of S in some way, right? Could I just differentiate S twice to get that? Isn't that what that is? And you are absolutely correct. If you're thinking that. Yes. So we said we had these two distinct relations, right? We had the ds over dt is V, and we had dv over dt is A. But I could also say that A is just when I take the derivative 2 times of S, okay? And we actually have a specific way to notate this, okay? So if y, right, so let's say if y equals f of x, right? Then if I'm finding the second derivative, right? So if I have, the first derivative and I want to take the derivative again, I can write this as d squared y over dx squared. And this means the second derivative. Okay, so this is, we would put 2's here and here to say that we're doing the second derivative of y, right? And we could even go further with this. We could do more. Instead of just doing the second derivative, I could do the third derivative. But the third derivative, right? So I would be taking the derivative again of d squared y over dx squared. But you're going to be surprised that the notation for that would just be this. So I just put a 3. It just, the d over dx part just becomes to the third power, right? Up here, I can rewrite this as d squared s over dt squared, which would be the acceleration. Okay. And so we can take the derivative more than once, right, of a function and this is kind of the notation we use, right? You may also be familiar with, or you might also see something that looks something along the lines of this. So if I have f of x, right? If I should have already introduced a prime notation, but if not, I'll kind of talk about it here. So if I'm taking the derivative of f of x, then this is the same thing as just f prime of x, right? So then if I want to do the second derivative of f, then this is the same thing as f double prime of x. And if I do the third, it'd be triple prime and 4 prime. Now, there's going to be a point, right, where you can keep going. You don't want to keep writing the derivatives. So oftentimes, we can rewrite the nth derivative of f as f parentheses on the top n of x. Okay, this doesn't mean I'm taking f to a certain power, right? So this is an n here. This doesn't mean I'm taking f to a specific power. This just means that I'm taking f, I'm differentiating f a certain number of times, right? So if I wanted to say the second derivative of f, I can just write f parentheses 2 of x, right? Or if I'm taking the 47th derivative of f, then this is the same thing as f of f47 of x, okay? So anytime you see something like this, right, f2, f4, whatever it is, that's what it's asking for, right? Of course, you could also just keep getting primed, right, fourth, fifth, etc. on it. And so that would also be a tell. But if we come back up here, right, y equals f of x, instead of writing f of x and putting the primes on it, I could just rewrite all of this as, so this would be y prime. I could call this y double prime, y triple prime, y quadruple prime, or I could write it similar to this. So I would say y1, y2, y3, y4. Okay. You can really choose whichever one's easier. Typically, outside of this class, I would just typically write a derivative using this y prime notation, just because I think it's the simplest way to know what's going on. But I want to show you all of them because, of course, if you're asked in the book or on a test to find these specific things, you'll know exactly what to look for or what it's asking for. Okay, so let's do some quick examples, right? Okay. So if we have the function y equals 3x cubed minus 2x plus 5, right? What happens then, right? We can see that if I take the derivative once, then y prime is going to be, I pull the 3 down, so 3 times 3 is 9, x to the second power minus 2 times 1 plus 0, right? So the 5 derivative of 5 is 0. And then I can take the derivative again, and I would call that y double prime. And this will be 9 times 2, which is 18 times x. And then the derivative of 2 is 0, so that's just 18x. If I do triple prime, the x becomes 1, so I just get 18. If I did 4 prime, then I would get 0, right? Because what's the derivative of 18? It's 0. So then we could keep going down, and then, but each time it would just end up, so no matter what n would be in that case, it would just end up being 0 from now on. Okay, so there's an easy example. So if we also have maybe the function y equals, well, they give 3 over x, which I can rewrite as 3 times x to the negative first power. Let's say I call this thing f of x, right? Then f prime of x would be negative 3 over x squared, right? And just to show that, I would have 3 times negative 1 times x to the negative 1 minus 1, which is negative 3 times x to the negative second power, or negative 3 over x squared. And then f double prime of x resorting to here again, I'm gonna get -3 times -2 times x to the -2 minus 1, which is +6, right? 3 times 2 is 6, x to the -3, or 6 over x cubed, and so on and so forth, right? Now, of course, it says the main, it says an advantage of this is just to be able to maybe write the derivative easier, because you'll notice when we were working it out sometimes and writing in parentheses on the side, it looked a little strange at points, but this is kind of an easier way to be able to plug in numbers and see what's going on. Okay, in this form. So if I wanted f prime of 1, then I could just put 1 in here or 1 in this one. Okay, so that's all that section is. Again, it's very short. There's plenty of examples to go through. You can practice. I think I only assign like 3 of them because I don't think, I mean, if you know how to do the derivative, then you can easily just keep taking it. But the discussion of notations is good. So, okay, good. Well, and with that, we've reached the end of chapter 2. Hope you've been able to get a lot of that out of it at this point. To kind of end our time here, because I do have quite a bit more time. I'm going to go through the last few problems on the study guide that I've made for you all. If you have not, I would encourage you to watch the first video that I've already posted on Canvas, which goes through every study guide problem except for 16, 17, 18, but I'll go ahead and do 16, 17, and 18 right now. So I'll let you be able to write that down while I pull this up for us. Let's see. Let's files. Okay, here we go. So so number 16 says to find dy over dx by implicit differentiation. Okay, so this is number 16. So number 16 says that x squared y cubed minus 6y is going to be equal to 25x. Okay, so what does it say? It says to find the derivative implicitly. So we're not going to solve this for y. I'm going to first just take the derivative of both sides. Okay, so when I take the derivative of both sides, I'm going to get that. Right, so first I have to do, so let's do this guy and this guy first. So the derivative of 6y, remember, I treat y as x and do the derivative that way, right? So the derivative of x is 1, so the derivative of y I would think at first is 1. So then I'm just going to be left with 1, but then I have to multiply by dy over dx, right? Since it's not x. So we have minus 6, okay? And then this is equal to the derivative of 25x. That is just x, so it just becomes 1. So we're left with 20. Okay. Now, we want the derivative of x squared y cubed. So to find the derivative of x squared y cubed, we have to use product rule. So I'm going to call this u, and I'm going to call this v. Okay. Maybe to help us, I'll write this on the side. U is x squared, v equals y cubed. So the derivative of u with respect to x, it's just x squared, so it becomes 2x. And the derivative of v with respect to x, we take the derivative of y and treat it like x at first, right? So we're going to get 3y squared. You can still see that, good. And then multiply this in the limited room I have by dy over dx. Okay, so product rule says that I take u times dv over dx. So that's going to give me 3x squared y squared times dy over dx. And then we have v times du over dx. So which is the same thing as plus 2xy cubed. Okay. So we are left with this as our derivative. right? So again, I want to get everything with the dy over dx by itself. So I'm going to get, I'm going to subtract minus 2xy cubed from both sides. So I'm going to be left with 3x squared y squared times dy over dx minus 6 times dy over dx equals 25 minus 2xy cubed. Okay. These both have a dy over dx in common, so I'm going to take that and pluck it out on the side. So this is going to give me dy over dx times, and we're going to have 3x squared y squared minus 6 left over, and this is equal to 25 minus 2xy cubed. And then what do? Well, just like the other problem, I want to get dy over dx by itself. So I need to get rid of everything that isn't dy over dx, which is this term. And so to do that, since it's all multiplied by dy over dx, I need to okay. So that's going to give me that dy over dx equals 25 minus 2xy cubed over 3x squared y squared minus 6. With this being our final answer. Okay, cool. Hopefully that makes sense. Very similar to the other example problem we did. So it should be good practice for the test on Wednesday. Okay, I'll leave that for a sec. Or I guess I can probably start erasing from the top down. So next, we were asked to find an equation of the tangent and normal line to the, what I call, what is the apple curve. And I might, maybe I'll try to show you this to you guys during class, but in person if I can, but if you have the Desmos app, please feel free to draw this on here. It does look like an apple. X squared plus y squared to the 3 halves equals x squared minus y. And we want to find tangent and normal lines at -1, 0. Okay, so if I want to find the tangent and the normal lines at -1, 0, right? We need two things. We need the point and we need one of the slopes, right? Because if I know one of the slopes, I can get the other one. We know the point, which is good, but I still need to get the slope, right? So now we get the slope, right? Definitely no easy way to solve this as is. So I'm going to take the orange, the derivative of both sides. So now we have to think about using chain rule, right? So now I have another function inside of a power. So first thing I need to do is I need to take the derivative of the outside part, which means that I need to take, so I'm going to put an arrow here. So I bring down this 3 halves, right, to the front. So I get 3 halves times x squared plus y squared, right? So I leave whatever that thing is on the inside to the 1/2 power, because I subtract 1 from 3 halves, which just give you 1/2. And then I multiply by the derivative of the inside. So what is the derivative of x squared plus y squared? Well, we've actually seen this already earlier today, right? In the last lesson, because when we talked about the circle, the derivative of x squared just gives us 2x. And the derivative of y squared is going to give us 2y, right? Again, because the power rule and we treat it like x, right? We do 2y, but then I need to multiply by dy over dx. Okay. And we want this to be equal to the derivative of x squared minus y. Well, what's the derivative of x squared? And just 2x. And what's the derivative of y? Well, if it was x, it'd be 1, but then I need to multiply by dy over dx. Okay. So notice first, one thing that might be nice to point out is that these terms both have a 2 in them, and there's a 2 dividing here. So I can go ahead and simplify a little bit to give us 3 times x squared plus y squared to the 1/2 times x plus y dy over dx equals 2x minus dy over dx. Okay, now it's quite annoying to have to carry around kind of this big chunk of a piece here that has to multiply to all my things. So I'm going to give it a name right now, if you'll permit me. Let's go ahead and call this guy right here. Okay, so I'll wrap it in an orange circle, and we'll call this u. Okay, so I'm going to rewrite this equation as 3u times x plus y. Sorry, I had to leave the dy over dx inside. Equals 2x minus dy over dx. I haven't changed the problem, I just gave it a name, right? That'll make my work a little bit easier as I go through. Okay. To solve this now, right? I need to take this 3u and distribute it, right? Because we don't want to have to deal with these parentheses. We might get parentheses later when we factor out the dy over dx, right? But what's my goal? My goal is to find the derivative. And to find the derivative, I need to get the dy over dx by itself. So I'm going to take 3u and multiply by both terms here. So I get 3ux plus 3uy dy over dx equals 2x minus dy over dx. Okay, so again, this is what I want to solve for. So I need to get all of its terms on the same side. And I need to get everything that doesn't have a dy over dx in it all on the opposite side. So I'm going to take this dy over dx and add it over. Good. And we're going to get rid of this 3ux. Awesome. So that's going to give us 3uy times, 3uy, my colors all here, dy over dx plus dy over dx, right? Because I just added it over. And this is going to be equal to 2x minus 3ux. Okay. Final step. These both have a dy over dx in common. And so that's going to give us, so we can factor it out. So we get 3uy plus 1 equals 2x minus 3ux. Okay. So now what do? Well, just like the other example, I need to take this thing and divide it from both sides. So I'm going to get that dy over dx equals 2x minus 3ux over 3uy plus 1, right? Well, what's u? Well, u is x squared plus y squared to the 1/2. So dy over dx in reality, once I put u back in, is equal to 2x minus 3 times x squared plus y squared to the 1/2 times x over 3 times x squared plus y squared to the 1/2 y plus 1. Okay, now this seems like what a hassle to be able to have to plug into, right? But let's remember what our point is. What's our point? It is -1, 0. So that means x is -1 and y is 0. So if it just has, so when I plug in my point, right? So dy over dx, and we want to evaluate this to get a slope at -1, 0, then I'm going to get -2, right? Because 2 times -1, minus 3 times -1 squared, right? Plus 0 squared to the 1/2 times -1, all over 3 times -1 squared plus 0 squared to the 1/2 times -1 plus, or sorry, this is y, right? So it's times 0 plus 1. Well, if this whole thing is multiplied by 0, this term just becomes 0. And then -1 squared is 1. 1 plus 0 is 1. So we get 1 to the 1/2, which is 1, right? And then 1 times -3 times -1 is +3. +3 plus 2 is 1. So the slope here actually becomes 1. Again, just know I won't give you one that's quite as difficult, maybe to plug in on the actual test, but it doesn't end up being too bad. The slope just ends up being 1, right? So that's pretty good. Okay, so having that now, I'm gonna work through this time. So we get the slope is 1, right? So we have the point 1, -1, 0, and we have the slope 1. Okay, so plugging into our point slope form, we get that y minus y1, which is 0, equals m, which is 1, right? Times x minus -1, which is x plus 1. But y minus 0 is just y, and 1 times x minus -1 is just x plus 1. So we get y is x plus 1. Good. Okay, what about the normal line? Well, the normal line in this case, right? So this is the slope of the tangent. The slope of the normal would be -1/1, which is just -1. So we're going to get y minus 0 again is -1 times x plus 1. Well, all that does is just changes the signs here. So we get minus x minus 1. So this is the tangent, and this is the normal. Good. Awesome. A little bit of work, but fun nonetheless. Okay. We got one more problem. Let's do it. If f of x number 18 says if f of x is 3 times x squared minus 1 to the cube, cubed, right? Find f double prime of 2. Okay, so I want to find the second derivative, right? That's what that means. We just talked about this. We want to find the second derivative of the function. So the first derivative, f prime of x, I take the 3 down and multiply it. So I get 9 times x squared minus 1 to the second power, right? And then I multiply by the derivative of the inside, 2x. I did do that right this time. Good. Okay. And I'll rewrite this just to make the derivative process find it easier. 9 times 2 is 18. X times x squared minus 1. Okay. What about f double prime of x? Well, I've used product rule, right? So let's call this term u, call this term v. So I take u times dv over dx, which is going to be 2 times x squared minus 1 to the 1 times 2x again. So this is dv over dx right here, just reaffirm, right? Plus v, which is x squared minus 1 squared times du over dx, which is simply 18. Well, that's going to leave us with, if I simplify, 2 times 2 is 4, 18 times 4 is 72. 72x squared times x squared minus 1 plus 18 times x squared minus 1 squared. But notice that there's an 18 in both terms, like that this was 18 times 4. I'm going to factor that out just to make your process of solving this a little easier. 4x squared times x squared minus 1 plus 18 times x squared minus 1 squared. Okay, and this is f double prime of x. Okay, so we started off by just having chain rule, but then we had to use product rule when we solve this. Okay, so now I want f double prime of 2. So I simply just get 18 times 4 times 2 squared times 2 squared minus 1 right? So maybe it would be more beneficial for us if I wrote the 2 in orange. Plus 18 times 2 squared minus 1 squared. Okay. Oh, I didn't mean to leave this 18 here. That should be gone by now, right? My apologies. 2 squared minus 1. Okay, so we plugged in the 2's. Sorry, I have to rush. I don't have a whole lot of time left. Apologies. So we get 18 times 4 times 4 is 16. 2 squared minus 1 gives us 3, plus 2 squared minus 1 is 3 squared is 9. And so then we can multiply this out. 16 times 3 is 48. So we get 18 times 48 plus 9, which is 18 times 57. And then that ends up being whatever the number is. Okay. If you didn't simplify exactly how I did and you just plugged into this, that's fine. But the ultimate goal is just to be able to get to whatever that number ends up being, which should be for everybody's time, 1,026. Okay, so pretty big number for the second derivative in reality, when the original value would be 3 times 3 cubed, which is 81. So kind of crazy. Okay, thank you so much for watching. Hope that helped out. That's all the solutions. I look forward to seeing you for the test. Hopefully it'll go well. You should have all the resources, hopefully to do as well as possible. Thank you for watching. Have a great day, guys.